اوكي. كانت الشاشه الثانيه شغاله عندي. All right. طيب بسم الله الرحمن الرحيم الحمد لله والصلاة والسلام على رسول الله. Yes, see. Okay, good. We're okay now. Bismillah. Yes, actually today we are going to start chapter 6, which is not part of your midterm exam, but we're going to finish all of chapter 6 and probably even chapter or most of chapter 7 before the exam, but these are not included in the major exam or the midterm exam. Okay, what's the title of chapter 6?
Quantum
theory.
Quantum theory. What's the meaning of quantum? Quantum comes from the word quantity. What's the meaning of quantity?
Related with numbers.
And what's the meaning of theory? Quantum theory. عشان كده سموها بالعربي
نظرية الكم.
نظرية الكم. But I wanted to understand what's the meaning of, what do you mean by quantum? It has certain quantity. That's the meaning of quantum. It means it has certain quantity. It's not any quantity. It has a certain value, and that's why they call it نظرية الكم or quantum theory. We want to learn about the quantum theory in this chapter, and there is a relation between the quantum theory and the electronic structure of the atom. We know the atom is consisting of what? 3 important items. What are these items?
Proton, neutrons, and electrons.
Where are the protons and neutrons?
The nucleus.
Nucleus, there is the protons and neutrons. How about where are the electrons? Outside.
The outside.
In the electron cloud.
Okay, in the electron cloud outside. And now, actually, we want to study where exactly are these electrons and what are their structures and so on and so forth. All of this depends on the quantum theory. Quantum theory means certain quantities, certain amount. Good. Okay. First, to study this, we will stay waves, all right? We know that everybody knows what are the structure of the waves.
Electromagnetic.
This is the wave. This is the wave, like this, like what we see in probably waves. There is in the water, we can see some of these waves and so on. These are waves, Okay, now the waves that we're going to talk about is in the electromagnetic spectrum. Electromagnetic spectrum. Why do they call it electromagnetic spectrum? Because this is the waves like this, but they call it electromagnetic spectrum because these waves actually consist of 2 waves perpendicular to each other. 2 waves which are perpendicular to each Other, by the way, are you recording? All right. Two waves perpendicular to each other like this. These waves, one of them is in the electric field, the other one is in the magnetic field. And that's why they call it electromagnetic radiation. Electromagnetic radiation. All right? Why do we call them electromagnetic radiation or spectrum? Why?
Because it has two
perpendicular.
perpendicular.
Two waves which are perpendicular. All right? And what's the name of this wave? One of them is in what?
Electric wave and the other magnetic wave.
Exactly, in the electric field. One of them in the electric field, and the other one is in the magnetic field. Good. Another thing we need to know about the waves, what do we call the distance from top to top?
Lambda. Wavelength.
Wavelength. How about if we take it from bottom to bottom?
Same.
Same
It's the
thing.
same.
How about if I take it from this point, to which point should I take it?
After 2 points.
Not this one, because this is going up, while this one is going down. It should be in this side. This distance, what's this distance?
Wavelength.
Wavelength, and they are related with each other. So the wavelength is from 2 points in the wave, which they are exactly in the same position. And this is called wavelength. We will call it from now on as lambda. All right? While this, from the trough here to the top of the wave, what do you call this distance?
Amplitude.
Amplitude, and we're represented by the letter A. Amplitude is represented by the letter A. You must know these names. Wavelength and amplitude. The wavelength is not the amplitude. This means we can have two wavelengths approximately the same distance. Okay, if we assume that this is exactly like the top, what's the difference between the A and B waves? They have the same wavelength, but they have different
Altitude.
Amplitude.
amplitude. Good. Good. Another important.
Doctor,
Yes.
shouldn't amplitude be from the top into the down, not into the half?
No. Amplitude is to the half.
Okay.
Here, amplitude. This is amplitude. Can you see amplitude? Good. Next, another important thing that we have to know, of course, the waves are moving. All the waves are moving. We want to know if we have a dot here. We want to know how many waves will go through this dot in a second. How many waves go through this point in 1 second. All right? Clear? Okay. This is called how many points are going through this, how many waves. This means we're going to count how many waves they're moving, so they will go through this point. This is called the how many waves go through this point in as 1 second. This is called frequency. nu. Frequency or nu. Clear? And we're represented by the letter V. Like V, it's not V, it's actually nu. This letter is called nu. All right? So, what's this?
Lambda. The wavelength.
Wavelength or lambda. What is the unit that we're going to use for it?
Nanometer.
Meter.
Meter or part of the meter, exactly, because it's length. All right? Okay, what's this?
Frequency.
New.
Frequency or nu. All right? What's the unit that we're going to use for it?
Hertz.
Hertz.
Actually, we're going to use second. In 1 second, this means second minus 1. Second minus 1. All right? Or there is a name for it, other name, which is called hertz. Exactly. So what's a hertz?
Second, the power of -1.
Exactly. Hertz is equal to 1/2, or second minus 1. Clear? Very good. And this is 1/2, because we're going to know how many waves per second. For each second, how many waves will go through this O. Good. Now, the amplitude, as we said, is vertical distance from middle line to top of the wave, which is, this is amplitude, and this is related to intensity. What is the meaning of intensity?
الشدة.
الشدة. Yes. All right. الشدة, or the amount of light. Amount of light. Amount of light. This means we have a lot of light. This means it will have high intensity and high amplitude. Okay, good. Now,
Doctor, but not every wave has light.
yeah, of course. No, we'll talk about this in a while. It's all light, but the light, it's not the visible light. That's all. Okay.
Oh, okay.
Yeah, good. Now, all this light, all the waves in general, and light in particular, but all the waves are moving with the same speed in vacuum. In vacuum, they have the same speed, which is what? This is the speed of light. It has been calculated to all these significant figures. Now, go to your periodic table and tell me what's written in your periodic table about the speed of light.
Velocity of light.
Yeah, what is it?
2.998.
To the power 8. What's the unit?
Meter per second.
Meter per second.
Now, is there a relation between the lambda, the frequency, and the C? Yes. C equal to lambda times nu. C equal to lambda times nu. Let's talk about the units. What's the unit for C?
Meter per second.
Meter per second. What's the unit for lambda?
Meter.
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 What's the unit for nu?
Second to the power minus 1.
1 over s.
1/2. Good. Is there any relation?
Inversely proportional.
Yes, they are.
Oh, they are the same. C equal, the units for C, m/s, and the unit for lambda times V times nu is actually meter over second. They are the same. Good. What does that mean? If this is constant. So what's the relation between lambda and nu?
C over V.
What's the relation between nu, C over what?
C over lambda.
Good. Clear? Now, let's solve this question. One type of laser, which is a light that you cannot see, of course, is used in the treatment of skin lesions. Okay? Neodymium doped yttrium aluminum grater, or NAG laser, NAG-YAG laser, is used for this treatment. This is type of laser, which is, we have in the university, we have machines that produce this laser, and we can do work with this laser for your information. Okay, now the wavelength commonly used for this treatment is 532 nanometer. What's the frequency of this YAG laser? What's the frequency?
C over V.
What? You have to say that C equal to what? Lambda times
lambda
nu. Okay, what's C? Look at the table.
2.998 multiplied by 10 to the power 8.
Plus 8 meter per second. What's the lambda? What's the lambda that we have here?
532 multiplied 10 to the power 9.
10 to the power minus 9.
Exactly, you have to multiply it by 10 to the power minus 9 to make it meter. Okay, and the only thing that we do know now is nu, which is per second. What's nu then?
C over lambda.
Okay, give me a final answer.
5.64 times 10 to the power 14.
What's the unit?
Hertz, or 1 over a second.
Or what? Or 1 over second. It's the same. Good. Excellent. Now, light that we can see is only small part, the visible light, I'll call it. What's the meaning of visible?
مرئي.
You can't see.
We can
see with
all the black thing that you see here is light. All of this is light distributed according to the wavelength. We can see only this part we can see. The rest of the light we cannot see. This is visible light, that the colored one is called visible light, all right? But we have light with a very low wavelength to very high wavelength, all right? In nanometer here, look, from here it is 10 to the power minus 3 wavelength to 10 to the power 13 nanometer. That the one we can see is only from 400 nanometer to 700 nanometer. From 400 to 700 nanometer we can see. If it's less than 400, then we cannot see. It will be in this range. And if it is more than 700, we cannot see also. All of this, after this arrows, we cannot see. We can see only this part of light, which is the visible light. Okay. Now, the frequency also, same thing. It's from minus 10 to the power plus 20 to 10 to the power 4. 10 to the power 4. And the one we can see is only the one with about 10 to the power minus 14 to 10 to the power minus 15, less than 10 to the power minus 14 to about 10 to the power, I mean, a very small range in frequency. Is this also clear? Good. What are the time? The visible, everybody knows the visible light, that the thing that we can look at and see. There is light which is more of energy. It's called ultraviolet. We usually to refer to it as UV. UV means ultraviolet. Ultraviolet. It has lower wavelength, okay, but higher energy, higher frequency. Okay. After light ultraviolet comes what? X-rays. X-ray is light. Everybody knows X-ray. What's X-ray?
أشعة سينية.
أشعة.
The thing that you receive usually in the medical centers, right? But you didn't. Did you see X-ray? Anybody saw X-ray?
Yes, I saw.
You can never see it.
No.
How can you see it? You can never see it.
Yeah, in the medical
X-ray, but
centers.
what?
In the medical centers.
Yeah, but you cannot see it. It's actually, it's invisible.
Yeah, you mean the waves?
Yeah, of course. You know about it, but you don't see it. Right?
Yes, light.
After that comes gamma ray. Gamma ray is the energy that comes up from radioactive material. Okay. On the other side, we have the light. What comes after it is the infrared light, IR light. And do you know where we use IR light? Where do we use it?
And remote controls.
Exactly. Remote control for television and so on is usually using IR waves. IR waves. Again, can you see the IR waves?
No.
Okay. After IR comes microwave. Do we know where is microwave?
Yes.
How do we use it? What's the application that we use it for?
The
Heating.
microwave.
What?
Heating food. Produce heat.
So actually, we use it in oven. What type of oven? Microwave oven. You know microwave oven. Everybody knows microwave oven. Yes, this is all one of the applications, of course. There is much more important application now. Where do you use it?
In our phones.
Cell phone, the one that we use is using microwave also. Do you?
And is it dangerous?
What?
Is it dangerous?
Of course, it's dangerous. But I mean, to some extent, and the amount they are exposed to is not that high. But it is, of course, dangerous. It's high energy. Of course, it's lighter energy than light, but it is dangerous. Is that when you? I mean, imagine that you put your hand inside the microwave. What will happen to it?
Oh, it will be.
It will be very dangerous, right?
Yeah, but we eat the food after putting it in the microwave.
Yeah, but what happened to the food?
It's be more heat.
Not only heat, we heat it, but we can even cook with it. We can change the whole thing. I mean, we can make a full.
The molecular will be.
So the molecules will change also.
Yes.
Same. Okay. Last thing, after the microwave comes the radio wave. Radio wave is used in radio. These are lower energy and lower wavelength. You have to know how the wavelength. If we go from this side to this side, what happened to the light wave, to the wavelength?
higher.
Increase.
Increase as you go from here to here, the light, the lambda increase. How about if you go, how about frequency? How does it go?
Decrease.
Decrease.
It is decrease.
Increase this way. Increase this way. Good. All right. Why do we call this light electromagnetic radiation?
Because it consists of two components.
Which is what?
Electrofield wave and magnetic field wave.
Now, very important experiment. We will talk about it and we will explain it to later on. This is called a very simple experiment. This is called double slit experiment. What slit means?
Cut.
A foil, maybe.
Opening. Slit means opening. So this experiment is about how many openings do we have here?
Two.
Two openings. That's why they call it what?
Double slit.
Double slit. Because it's two. This is the first slit and this is the second slit. Now, the property of light, when you have one wave like this and the other wave exactly like this, what will happen? They will add to each other. Right? And when you have one wave like this and the other wave like this, what will happen?
They will cancel each other.
Cancel each other.
They will cancel each other. And that's this experiment. The whole thing, when you put light goes through these two slits, it will scatter like this, and there will be time in which the light add in certain points and will cancel in certain points. And the one with white, what happened?
The waves will be added.
Added. How about if it's dark like this?
They will be cancelled.
And it's become like this. Added, cancel, added, cancel, added, cancel, added, cancel. And that's how you can see the waves, how they are canceling or adding to each other. Can you see them? Good. So how do you do this experiment? You bring light and expose it to these waves, and you'll have these results.
Okay.
After a long time, they repeated this experiment. Next time they repeated the experiment, using electrons. So they had electrons coming out from here, and the electrons went through this double slit light, and they found exactly the same result. Uh-oh, what does that mean?
Electron has two nature, physical and wave.
Of course, we always think about the electron as a particle. If it's a particle, it should go through this and go inside and hit the wall. But they found the same result like this one. This means it could be particle, but electron could be what?
A wave also.
Wave. The electron could be wave. What's the name of this experiment?
Double slit experiment.
Double slit experiment. Double slit experiment. Why this experiment is important from electron point of view? Because we found that actually it applies also to what? To electrons and make them waves. Good. Next. Black. body radiation. Black body radiation. This is experiment. All I want you to know is the name of the experiment. What's the name of the experiment?
Black body.
Black body radiation. What's this experiment? They took a black body, black box, like this, very black box, and they heat it a lot, and then let it cool down. When it's cooling down, what will happen?
It will emit light.
There will be يعني خلونا نجيب لكم اكسبيرمنت بسيطه. لو اخذت طابق البيض وحطيته على النار مده طويله ايش حيصير له بعد شويه؟
ينفجر.
طابق بيض على نار حيصير مثلا ابيض حيكون لونه يصير كيف شكله؟ يكون احمر صح؟ Alright? That's the experiment. They took black box and they heat it until it become very hot. Then they start studying the radiation that's coming out. انت لما يصير احمر لو قربت يدك منه من بعيد يدك حتشوف الحراره تجي من الحمره، حتى لو شلته على النار حتشوف من الحمره تجي الحراره على يدك صح؟ Why? Because heat is coming out of the box or or whatever. Clear? Heat is coming up. They study this heat. They study this, they call it radiation. They start studying this radiation that's coming out of black box. And
Doctor,
yes,
why did they use a black box?
to have more heat. All right, and they call it black body radiation because they want, you know, black can absorb more heat than white, right?
Oh, okay, yeah.
And that's why they use black body radiation. The experiment, as I said, is extremely simple. Heat black box and then study the radiation coming out. This is called black body radiation experiment. That's it. When they study this, a great scientist, his name is Planck. Planck, you have to memorize the name extremely well. Planck. Planck. All right? He said the radiation that's coming out, there is small quantity, discrete quantity. Discrete quantity. What's quantity means?
كمية.
And what's discrete?
متحفظ.
No.
Separated.
Small amount.
Very small, very small, very small. Discrete means extremely small and it has a minimum. He said that the energy has a small, very small amount, very discrete amount, and he came up with this amount, and he said the minimum energy that you can have is called H, which is Planck's constant. This is the minimum amount of energy that you can get. All right? And he said that the energy is actually a multiple of the frequency by this quantity, by H. So I want you to memorize this equation very well. What's this?
Energy.
Energy. What is this?
Frequency.
Frequency. And what is this?
Planck's constant.
Doctor, is it called photons?
No, it's not photons. This is called, we're talking about energy now, not photons, only energy. All right? We'll talk about photons in a while. This Planck's constant was calculated and it's available here. That's H. I want you now to go to the periodic table again. Do you see H in your periodic tables?
Yeah.
6.626.
6.626. 6.626 times 10 to the power minus 34. What's that? What are the units?
JS.
Joule second per particle.
Joule times second, and of course per particle, of course. All right. What's the unit of frequency?
Hertz.
1/second. If you multiply joule times second times 1/second, what will be the unit for E?
Joule.
Joule. What's the energy unit? Joule. That's exactly the same. Good. Now, we know that frequency is equal to what? C over lambda. So, energy is equal to what?
HC over lambda.
HC over lambda. You have to memorize. Of course, you need to memorize this one definitely. Okay, but it's the same. You can write it this way as well. Clear? All right. Now, if we have a light which has 532 nanometer, a light which has 532 nanometer, what's the energy of this light? We know that energy is equal to what? H nu or
C over lambda.
HC over lambda.
Lambda.
Go to your periodic table. What's the value of H?
6.626 multiplied by 10 to the power minus 34.
Good. Go to your periodic table. What's the value of C?
2.998
2.998
to the power multiplied by 10 to the power 8.
8. Don't forget this is meter per second, and this is joule second. Joule times second. Good. All of this divide by what?
Five, 3, 2 times 10 to the power minus 9.
Power minus 9 meters. Exactly. All right. Now, calculate. The meter will go with meter. Second will go with second. What will be left?
Joule.
Okay, calculate the energy quickly.
3.7.
Times
10 to the power minus 19.
10 to the power minus 19. 3.7 times 10 to the power minus 19. Good. All right. Next, do the same thing for 632 nanometer. Can you do the same? What's the energy now? Equal to HC over lambda. Lambda now is 635.
3.128
128
times 10 to the power minus 19.
Minus 19. And then he wants to have, what's the difference? How much energy of photons in the green light waves greater than red light? So what's delta E? This is E1.
We subtract
subtract, give me an answer.
0.572 times 10 to the power of minus 19.
Exactly. So you can calculate it, take the difference between this one and this one. That's it. Is this clear?
Yes.
So,
Yes.
Good.
Yes.
next. So this is the final answer is 6.1. Somebody gave me another number. So there is a mistake there. You told me here it's 3.7 and 3.1. Yes, exactly. 3.7, 3.74 and 3.13. The difference is this. Good. Next. Another very important experiment. It's called photoelectric effect. Photoelectric effect. You have to memorize this. The name of the theory. What was the first experiment that we talked about?
Double slit.
Double slit.
Double slit. The second one.
Black body radiation.
This is the third one. What's the name of this one?
Photoelectric effect.
Photoelectric effect. All right. And who did this one? Probably the most famous scientist. Who is it? Einstein. There is a problem this point. No problem. All right. What's this experiment? Okay. He has metal in 2 electrodes. All right. And he has this evacuated. This thing is evacuated. What's evacuated means?
There's no any air particles.
No air.
No air inside. All right. And then he has electric voltage like this. And then he hit it with incident light. Incident light. I mean, he hit this rod with light. Okay. What did he notice? That when he hit it with light, the electrons will come out. Electrons will come out. Is this clear? Okay. So when he hit it, the electrons will come out from the plate, not from the plate. I think I made a mistake. See, the light will come out, hit the plate. This thing is plate here, and this one is a rod. It will come out from the plate as electrons will come out like this. That's the experiment. So what's the experiment? He has plates like this, and he hit it with light. These 2 plates are connected to electric source, to a battery. Okay, and then he hit this thing with light, the electrons will come out. He starts studying these electrons that is coming out, and he called this photoelectric effect. Because why did he choose the word photo? Because it's coming
Photon.
from light. Photo means light, right? And what's electric? Because it's coming from battery. And the electrons are coming out as part of the electricity. So that's why they call it photoelectric effect. All right? What's the most important thing? The light, the electrons will come out of the plate. Electrons will come out of plate provided we have minimum frequency. Okay? It does not depend on the amount of light for the electron to come out, which is like this, the electron to come out, depends on what? frequency,
Frequency.
not on intensity, which is amplitude. Is this clear? The amplitude is related to density. So in order for the electron to come out, this depends on what? Frequency. Frequency of the light. So frequency, not on the amount, not on amount, not on amount or A, not on A. Intensity is amount. Is this clear? So what did we learn from photoelectric effect? That the electron will come out only depending on what?
Frequency.
Frequency, not on amount or not on
intensity.
Intensity or amount is the same thing, or amplitude. Good. And he said that why the light, that is light. We know if I hit you with a light, what will happen to you? What will happen to you?
Nothing.
Nothing, right? If I hit you with light, supposedly there should be nothing happening. But why the light here is taking the electron away? Einstein proposed that maybe light is not a light like this. The light is actually particles like these. These particles are called now
Photons.
These photons will come and hit the electron, and what will happen to the electron if I hit you with a ball? Are you going to feel it?
No.
لو واحد شات كرة على بطنك مثلا ما بتحس
yes.
ما بتحس بالضربة؟
Yes, I will feel it.
ولكن لو جاء لايت على بطنك, you will not feel anything, right?
Right.
That's why Einstein said yes, because the light is consisting of photons. These photons, when they hit the electrons, what will happen to the electron? It will come out. And he called these particles as photons. Photons. And of course, the energy of the photon is like what proposed by black body radiation is equal to h nu. Is this clear? Good.
Doctor,
Yes.
when they hit the electrons, are photons positively charged or
No.
no?
No, they are neither positively or nor negatively. They are not charged.
Okay.
Then Einstein came up with an equation, very important equation, which is this equation. H nu, I'll write it here again, is equal to kinetic energy plus W. And explain to you everything now. Okay? What is H nu?
Energy.
Energy.
The energy of what?
Photon.
Energy of photon or energy of light. Photon is light, right? Good. Next.
Right.
If you think about the electron is like this. Where is the electron here? This is the electron, and this is what's this?
Nucleus.
Nucleus. Okay? And what's the power that's holding this together? It's called
Nuclear force.
binding energy. All right? Which is, in this time, we're going to represent it by W. So what's W?
Binding.
Binding energy.
Which is what? The force that's holding what? To what?
Electron to its nucleus.
The nucleus. This force is called binding energy. Is this clear?
Yes.
Force that's holding the electron to the nucleus is called binding energy. And what's Ke? Everybody knows Ke, kinetic energy. Okay, what's this theory saying? That when you hit the atom with energy like this, what will happen? You need to have minimum energy of what? W, okay, to make the electron come out. So that you need to have energy equal to the energy that's holding these together, which is W, and to make the electron comes out. When there is more energy, what will happen? The electron will start moving faster. And that's why this is kinetic energy. So I want you to memorize this equation. And this equation, Einstein got Nobel Prize on this equation. Okay, let's explain it very well. What's E?
Energy.
Energy of what? Of light.
Binding.
What's H?
Planck constant.
What's mu?
Frequency.
Very good. What's W?
Work.
Binding energy.
Not work, binding energy. What type of binding energy? Holding what to what?
Electrons to nucleus.
Exactly. What's Ke?
Kinetic energy.
What do you mean by kinetic energy? The speed the electrons will come out with. Is this clear? Good. Calculate the energy of a photon with a wavelength of 5.00 times 10 to the power 4 nanometer. Can you tell me what's energy?
H times C over lambda.
H over C over lambda. Good. H. Get it from the periodic table quickly. Times what?
E, which is 2.9.
998.
By what?
3.97 multiplied by 10 to the power minus 21.
Why did I write here 10 to the power minus 5?
Is you multiplied by minus 9.
Minus 9.
Minus 9 plus 4.
What's the answer?
3.97
multiplied by 10 to the power minus 21.
What's the unit?
joule.
Okay. A photon with a wavelength 52 nanometer, ultraviolet region, 52 nanometer. This one was infrared, that's the wavelength, and this is ultraviolet. What's the energy? Quickly, I need an answer, final answer. Okay, what's the energy here? Quickly. You have H, you have C, and you have the wavelength multiplied by 10 to the power minus 9. Final answer.
3.82 multiplied by 10 to the power minus
18.
Minus what?
18.
18 joule. Good. Now, calculate the kinetic energy of an electron ejected by a photon in part B. Okay, from a metal with a binding energy of 3.7 electron volt. What's this binding energy?
W.
W. Can you change the electron volt into joule? This is the unit. What are you going to do? What's the energy in joule?
We'll multiply it by 1.6.
That's W in joule. Calculate W. Just multiply 3.7 times this number. Give me answer.
5.927.
927 times 10 to the power
Minus 19.
minus 19. Okay. Anybody got the same answer?
Yes.
Yes, miss.
Multiply this
Yes.
by, as I said, symbol. Okay, good. Now, what will be the kinetic energy of the electron when it comes out? If it's hit by E, you don't see.
Subtract.
Subtract what from what?
E from the
B minus C.
3.2 times 10 to the power minus 19 divided by or minus 5.927 times 10 to the power minus 19. And I need an answer.
3.2 times 10 to the power minus 18.
Who got the same answer?
Yes, doctor.
Yes.
So 3.2 times 10 to the power minus 18, and actually 3.2 times 10 to the power minus 18 is the answer. Okay, good. Are you following?
Doctor.
Yes.
Doctor, does the photon have a mass or no?
Well, of course, if it's a body, then it is a mass. Yes. That's the difference between mass and wave. The wave has no mass, but it has wavelength. The photon have mass, but no wavelength. But Einstein proposed that the photons is something like this, in which it has both the particle, it's a particle with waves inside it. So it's not exactly clear how is it exactly. But if it is photon, it has a mass, yes.
Okay, thank you.
Next, line spectra. I want you to memorize the word line spectra. Okay, what's the meaning of line spectra? I can make it very easy for you to explain. It's actually like picture. Line spectra, you can think about it. Why they call it line? Because it actually is going to be lines like this. Lines like this, all right? And these lines are called line spectra. But what does it mean exactly? It means picture. Now, if I take any one of you and take a picture for him, what are you going to see in the picture? The picture of that person, right? لو خدت صورة لأي واحد شفت الصورة ايش هتقول؟ هذه الصورة لمين؟ للشخص اللي خدت له الصورة صح؟
صح.
Exactly. That's what's the meaning of line spectra. Exactly. That's the meaning of line spectra. What did they do? They took hydrogen, okay, and this is they have hydrogen in here, H atom, not H gas, H atom only. All right, and they hit it with light. Of course, this is evacuated. Discharge. Discharge means what? Evacuated. All right. Next, they hit it with light, and they collected the light like this, and they came up with these lines. These lines here are called line spectra. So what's the meaning? Line spectra. What do I mean? I mean they did the experiment for many hydrogen atoms, not one. They took another hydrogen atom, not, of course, you can never have one, but many hydrogen atom here, and then they did it in another place, and they did it in another country, and in another country, and in another country. They always come up with these lines like this. And so when you see these lines, what are you going to understand?
It's hydrogen for hydrogen.
These lines are for hydrogen only. Is this clear? Okay. What's the name of this? What are these lines called?
A line spectra.
Line spectra. You have to memorize the name. Line spectra. And if they are many, we call them sometimes line spectrum. Spectrum means a lot. Spectra for one and line spectrum for many. But it's the same word. All right? Good. These lines are called spectra, line spectrum. And now, when you see, if I give you another table and I show you 1, 2, 3, and 4. If you see these lines right away, what are these lines represent?
Hydrogen atom.
Hydrogen atom, H atom, not H2 gas, hydrogen atom. Okay, they did this for other elements and they found all these lines. Look at the line of lithium. See, it's different from hydrogen, right? Can you see it? And then the line of sodium is like this. Line of potassium, these are the line of potassium, calcium, strontium, barium, hydrogen. Did we see this before? Did we see this before?
Yes.
Yes, just a while ago. All right. And then helium, neon, argon, all of these has been done. And you can see here, each one has a certain shape, certain lines. These are blue and yellow lines and so on. These are exactly, these lines, for example, for this one, we will always see them for which element?
Lithium.
For lithium, and so on and so forth. Clear?
Doctor, even for the isotopes?
Of course, even for isotopes. Excellent question. Yes, you will see them the same thing even for isotopes. It's hydrogen atom. You will see this line for hydrogen atom, or which is H11, or H12, or H13. They're exactly the same. Okay, clear? Good.
Doctor,
Yes.
is it like some method for matching the blood?
It's like picture. You know what's the meaning of picture? This is
like a fingerprint.
Like a finger. Oh, that's much better even. This is like exactly like fingerprint. Exactly. Oh, I like this. I did not think about it. It is
It's an ID, doctor.
like fingerprint. Exactly. So this is the fingerprint of hydrogen, if it has fingers. Clear? Very good. Then somebody, I want you to memorize the name again. What's the name? Rydberg. Rydberg. All right? Came up with equation to represent the lines of the hydrogen. These lines, he studied them and came up with equation which is 1 over lambda equal to R times 1 over N1 square minus 1 N2 square. What's lambda?
Wavelength.
Wavelength. And what's N1 and N2 are the lines. So he took these lines, 1, 2, 3, and 4. He called this one 1, 2, 3, and 4. And he came up with an equation and came up with a constant, which is called, what's the name of the constant?
Rydberg's
Rydberg.
Rydberg constant. Rydberg constant. And this is the constant. Of course, never ever memorize it. That's Rydberg constant. Okay. What's the unit for Rydberg constant in this case?
1 over meter.
1 over meter. Why is it 1 over meter? What's the unit for 1 over lambda?
1 over meter.
1 over meter. That's why. What's the unit for n? No units. It's what? No, numbers. 1, 2, 3, 4 only. These are numbers. Clear? Now, then another scientist, you have to memorize the name, Bohr. Bohr, you have to memorize the name. He came up with the same theory like Rydberg. He said that why do we see lines like this? Okay, because the hydrogen atom is consisting of orbitals. First orbital, second orbital, third orbital, fourth orbital. And the electron, there's more, of course, but we cannot see them. If you put more, you can put more orbital. The electron of this is the hydrogen atom now. Hydrogen atom. Hydrogen has 1 proton here and 1 electron. Where is the electron? The electron is here. Okay? When you give it energy, the electron will jump from n equal, we call this one n equal to 1, like these numbers. We said this. Remember 1, 2, 3, 4? We call them n, each one. This is n1, n2, n3, n4. Clear? He came up with, made them circle like this, n1, n2, n3, n4. So this is n2, this is n1, 3, and this one, n4. And in the hydrogen, the electron is available here. Now, if you give it the energy, the hydrogen will jump from n equal to 1 to n equal to 2 without stopping in the middle. If you give it more energy, what will happen? It will jump from 2 to 3. And if you give it more energy, it will jump from 3 to 4. What will happen if it goes from 3 to 4 and from 4 to 3?
Release energy.
Release energy.
So going from 4 to 3, is it exothermic or endothermic?
Exothermic.
Exothermic.
Exo. Exactly. But going from 3 to 4 or from 2 to 3, let's say, if it goes from 2 to 3, is this exothermic or endothermic?
Endothermic.
Endothermic.
And he came up with this proposal. That's the guy called Bohr. He got Nobel Prize for making this proposal, and he came up with this energy of each line. This constant is Rydberg constant, RH constant. We know about this. What's the name of this constant?
Rydberg constant.
Rydberg constant. You have to memorize the name, not the value. The value is available. Look at your periodic table, you'll find the Rydberg constant. Okay, and what's E?
Energy of
energy of the circle here. What's N?
Orbit.
Or number, actually. N is equal to what? 1, 2, 3, 4, 5, and so on and so forth. Which is, this is 1, 2, 3, 4. There could be another circle, 5, 6, 7, 8, 9, 10, 11, 12, whatever. Is this clear? And he came up with these things. Now, when the electron is in one, when the electron of the hydrogen is in one, this is the hydrogen, this is n equal to 1, and if the hydrogen is n equal to 1, they call this one ground state. When it is in higher level, it's the same hydrogen, but it's not now in N1, it is in N2. This is called excited state. Why? Because the electron gains some energy and went to n equal to 2. When it is in N3, what will happen? What we are going to call this one now? Also, excited state. So, how many ground states we can have for hydrogen?
One.
Only one. How many excited states?
Unlimited.
Infinity.
Many. We can have anything. What do you call the first one? We call it first excited state. What's the second one?
Second excited state.
The first one. Third. And then he says, Bohr, that the electron can jump from n equal to 1 to n equal to 2 without stopping in the middle. And that's why he came up with a proposal like this. So the hydrogen, the electron can jump from here to here, and jump from here to here, and jump from here to here, jump from here to here, and so on and so forth. But it cannot stop in the middle. Can the electron stop here? Can it stop?
No.
No.
No. And that's why they call it quantum. Quantum means certain quantity. It has to go through certain quantity. It can go from here to here, and it can't stop here. It can stop here, no problem. And then it can jump from here to here, and it can stop here. And it can jump from here to here. Yes. Can it jump from here all the way to here?
Yes.
Yes, it can. Yes, it can. But it cannot stop in the middle, like here. Can it stop here? Or can it stop here? No. It can jump from here all the way to here. How about from here all the way to here? Can it jump?
Yes.
Yes, it can, but it has to be on certain level. Okay? And the difference in energy between the first one and the second one, because you know this equation calculate the energy of each level. This equation calculate the energy of N1, N2, N3, N4. How can I make delta E between N1 and 2? What is it equal to?
E2 minus E1.
Times what? 1 over from 1 to 2. From 1 to 2. So what should I write?
1 over 1 minus 1 over 4.
No, always from 1 to 2. You put first what?
4.
2.
2 square minus 1 over 1.
Doctor,
Yes,
could you take attendance?
sure I will. Okay, so I want you now, while we're doing this, I want you to calculate what delta E. If you go from 1 to 2. Okay, I will take attendance right away. Okay, it's open now. You can take attendance and leave.
Doctor,
Yes,
why we use minus in the law?
go ahead. I want you to tell me. As we said, if you go from 1 to 2, is it endothermic or exothermic?